now we will move on to the lecture notes, okay? Let's recall what is sample space. Sample space is basically the set of possible value, okay? Or the set of possible outcome. What is a random variable? A random variable, denoted as RV, is a variable that takes a value from a sample space with a specific probability. So suppose I have a sample space, now I use curve X. You can use whatever symbol to denote a set. Usually in set theory, you use set A or set B or set X, okay? But now we will use this symbol as a random variable, so you need some other symbol to denote the sample space. So we can use the omega. So I will use this calligraphic X to denote the sample space. Let X be a random variable over the sample space calligraphic X. Okay, here is a split function expression of RV. That means a split function expression of this random variable X. So it's saying that X has the probability half, give us 1. X has the probability that 1/4 give us 2. And X has the probability that 1/4 give us 3. So actually we can plot this. So here, this x-axis is a small x. We have 3 probability. That's small x is 1, small x is 2, and small x is 3. So for small x is 1, the probability will be half. So let's say this represents half. And then for small x is 2 and 3, we both have probability 1/4. So let's say 1/4 is half of the height. So it will be somewhere here. So that means 2 and 3 both like this. So this picture is the plotting of this random variable function. And then let's say we go back to this example. The calligraphic X is the sample space. It means the possible outcome of this random variable X is 1, 2, 3. Is it possible for X to give you 5? No. Is it possible for X to give you -6? No. So here, X is a symbol that denotes the random variable, okay? It's not a set. And then this big X, capital X equal to the small x is meaning that this random variable X is taking a particular value X. And this has a name called realization. A sample is called a realization of the random variable. A realization is just a fancier term of observed value. So for example, a 2-sample realization, that means we have 2 data points, 3, 3. And a 4-sample realization, for example, is 3, 3, 1, 2. A probability distribution we write as P capital X equal to small x. This is basically the mathematical notation of random variable. It means the probability that the random variable X takes the particular value small x in the calligraphic X, the sample space. So using this notation, instead of this split expression, we can write it as a function. And if I have this function, I can plot it like this. Sometimes people will use compact notation. For example, they don't want to write this double bar P capital X equal to small x. They just write a small px. So this is a compact notation. So basically it means the same thing as this notation, but we just write like this. For the axiom of probability, there are 3 axioms, and there's an axiom 0. I name it as the sample space is non-empty, okay? And then these are the 3 axioms. Basically means any probability is non-negative. Probability of sample space is 1, and if the events are disjoint, then we have some rule, and if the events are not disjoint, we have inclusion-exclusion principle. And here's an example. Suppose I have the probability of random variable X equal to 1 is A, and the probability of random variable X is 2 is B, and the probability of random variable X equal to 3 is C. Find the probability that random variable X is larger than or equal to 2. So, by definition, X larger than 2 with respect to the sample space is the same as the set 2 union of the set 3. Then by inclusion-exclusion principle, then this expression is the same as this expression. And then we know that this is actually empty set. The probability of empty set is 0, so therefore 0 here. And then the probability of X is 2 is B, because we have already divided the probability of X is 2 is B. The probability that X is 3 is C, so therefore we have B plus C minus 0, that means B plus C, okay? We also have the product rule. For example, the probability that the random variable X takes the value in the set A1 and also X takes the value in the set A2 will be the probability that random variable X takes the value in set A1 multiply the probability that random variable X takes the value of A2. And we also have the complementary rule. Okay, this one is an important formula. Okay, this one is an important formula. So the probability that the random variable X is smaller than a particular small x. Okay, notice that this is strictly smaller. It will be 1 minus the probability that the random variable X is larger than or equal to X. And of course, similarly, we have probability of the random variable X strictly larger than small x equal to 1 minus the knot of this statement, that is X smaller than or equal to X. Here's an example of this complementary rule. Suppose I have a random variable X that is strictly between A and B. That means strictly larger than A and strictly smaller than B. Then what does it mean? It means I have a probability of the X is strictly larger than A and strictly smaller than B. And because of the product rule, I can split this into this expression, that is the probability of X strictly larger than A, compute this, and then multiply with the probability of X strictly smaller than B. I compute this, okay? And then how do I compute these two, each of them? I can use the complementary rule by using 1 minus the not cases. I have this term for the X strictly larger than A and have this term equal to the X strictly smaller than B.